Okay, this lecture will be from your Carlton book, and this is Chapter 2 on radiation concepts. You have some objectives that you'll need to be able to answer. Make sure that you understand what is being asked and being able to answer these. Oops. So looking here, when we talk about radiology, it's actually viewed as an art. There's scientific method, and it's considered a natural science. So there's also physical science and biological science. So with physical science, we're talking about non-living matter. So we're talking about physics. With biological science, we're talking about living matter. So anatomy and physiology. So with radiography, we combine both. So we talk about the physical science with the biological science also on the effects of the actual physics of electrons. So when we talk about matter and energy, so physics studies the relationship between the matter and the energy. So matter has mass and occupies space. So mass is the quantity of matter contained in an object. So weight is the force that an object exerts under the influence of gravity. So if there's no gravity, there is no weight, but yet there's still mass. So important to be able to understand that. Energy is a force used to do work. So if we look at the structure of matter, so there's mixtures and substances, and it goes into elements and atoms, and there's compounds or molecules. And when we talk about that, we go into substances. And first thing we'll talk about is simple, which are elements, and they cannot be broken down into simpler substances. So there's 92 naturally occurring elements, such as, hydrogen, oxygen, and all the different things on the periodic chart. There's complex, which are compounds when two or more elements are united. So it's when we take two of the simple elements and we combine them together and into compounds. So like H2O is a great example. Sodium chloride is another example. So when we look at atoms versus molecules, so when we talk about atoms, they are the smallest particle of an element that still possesses the chemical properties of the element. So the molecule is the smallest particle of a compound that still possesses the characteristics of the compound. So atoms are tightly bonded to one another when a molecule is formed. So they bond together by attraction, so the negative and the positive. So they're bound together by that attraction. So the degree of attraction determines if it's a liquid, gas, or a solid. So it's largely controlled by temperature also. So it's the degree of attraction and largely due to temperature. So if we look here, this is two hydrogens and an oxygen, so this is water. So if we look at energy, what is it? It's the ability to do work. It's measured in joules. So if we look at radiation, its energy is emitted and transferred through matter. So it's in the form of heat and light, and matter is struck by a form of radiation energy. It is described as being exposed or radiated. So the laws of conservation of matter and energy, this is E equals mc squared, where E is energy, m is mass, and c is the constant, and the constant is the speed of light. And it's Albert Einstein's theory of relativity, and it describes the relationship between matter and energy. The sum of all matter and energy in the universe is constant. So matter and energy cannot be created nor destroyed. It can be converted from one form to another. So when we have the electron going across the X-ray tube and it hits the target, it's converted. It's not destroyed. It's converted to photons and heat. So it is changed. So it cannot be destroyed. So looking over the historical overview, we have the ancient Greeks, basic air, water, earth, and fire. Then we go into Dalton's theory, which is separated elements based on mass, which led to the development of the periodic table by Mendeleev. Then we have the Rutherford, so dense positive nucleus surrounded by a cloud of electrons. So he's the first one to say, hey, there's something more to this. There's a nucleus and there's a whole thing of electrons all around it. And then Bohr came up with the miniature solar system, where it has the nucleus with all the electrons circling out in orbit. There's the Schrödinger, which is the foundation of modern physics. So it's the quantum physics or wave mechanics. So when we talk about atomic structure, when we look at the nucleus, so the nucleus we have here, so here in the center, this is your nucleus. These are electrons that are circling the nucleus. They're out in orbit. So the nucleus is a small, dense center. It contains nucleons, which nucleon is protons and neutrons together. So almost all of the mass of an atom. So an electron is basically got a mass of 0. It is so small that they consider it 0. So all of the mass comes from the nucleus, from these nucleons. So an electron is out in orbit. So these guys are circling the nucleus, which is nucleons of protons and neutrons. So quantum physics. So electrons cannot be divided. Protons and neutrons are made up of quarks. So the string theory, or the M theory, links quantum physics to relativity. And you can read about that in your book. It goes into it. So the basic atomic particles, there's the proton, neutron, and electron. So the proton, pro, means positive, so it's positive charge. Neutron is neutral charge, and the electron is a negative charge. The atom is electrical stability is maintained through equal number of protons and electrons. And the atomic number, which is the Z number, distinguishes the elements by number of protons contained within the nucleus. So the protons control the atomic number. You change the atomic number, you change the element. So what that means, if you change the protons, you change the element. So one example that they give is radioactivity. So if you have radioactive decay, so radium with the atomic number of 88 emits an alpha particle, which is a big heavy particle, which changes it as it decays to radon, which has an atomic number of 86. So other variations, so there's isotopes, so it's changing the number of neutrons or electrons. It does not change the element. Only changes in protons change the element. So if we're changing the neutrons or we're changing the electrons, we are not changing the Z number. So only changes in protons. Ionization, or an ion, it's addition or removal of an electron from an atom. X-ray photons can interact with atoms, results in an ejection of an electron. So everything we're going to be learning about is how an X-ray photon interacts with the electron cloud and what happens and where it's knocking that electron out. So it interacts with it. It's either absorbed or the electron is kicked out. So it changes the charges between the atoms. So there's either going to be a negative or a positive to it. They either absorbed an electron where it's going to be a positive charge, or it lost an electron where it's going to be negatively charged. So X-rays and ionization. So ionization of atoms causes disruptions in bodies' metabolic relationships. Exposing the patient to ionizing radiation thus requires an order from a licensed physician. So we're changing the body makeup, so the metabolic relationship of the body, by adding or removing these electrons. So we need to have an order from a licensed physician in order to do this. Okay, so you can see here ionization. You can see a photon coming in. So here we've got a wave, and we've got a photon coming in. It hits an electron and knocks it out. So you have a free electron, and then you're short an electron in your electron cloud. So it's knocked this thing all the way out. So it can go in any direction. We call this our scatter. So it can go in any direction and makes this unstable because it's now negatively, actually it knocked out a negative, so it's positively charged. Okay, atomic mass, so concentration in the nucleus. So the mass of a proton is 1,836 times greater than an electron, where mass of a neutron is 1,838 times greater than an electron, so it's quite a bit. When we talk about atomic mass number, it's abbreviated by the A, and it's a number of protons and neutrons in the nucleus. So the proton and neutrons of the atomic mass is of 1. So neglects mass of the atom's electrons, so they consider the electron as having a mass of 0, so it doesn't have any mass to it. The mass it does have a little bit. It's so small and it negates itself. All right, so orbital electrons. So Electrons around the nucleus are in continuous motion, so it defines the location where electrons might be at any given time. So distance from the nucleus determines the energy level or the shell. So the shells, you'll hear me refer to them a lot as K, L, M, N, O, P, Q. Those are the shells, but the K is the first shell, the L is the second shell, the M is the third shell, the N is the fourth shell, the O is the fifth shell, the P is the sixth shell, and the Q is the seventh shell. So there's a formula for calculating how many electrons can be in a shell. So the electron capacity is 2 times the number of the shell to the second power. So that's how you figure out how many electrons are in a particular shell. So if we look here, the electron binding energy, which is E to lowercase b, energy needed to eject an electron from the atom. It's related to how close the electron is to the nucleus. So the electron binding energy increases as the Z number increases. So if we look here, we have your nucleus, and here's your K shell, which is N1. And this is tungsten. I know that because 69.5 keV is what's required. It's about that, or above. And then here we have 2 electrons. And then because N times the number squared is 2. And here we have about 12 keV. So you can see it drops down in the energy quite a bit as we head out to the outer shells. Okay, so that's how that works. So 2, 8, 18, 32, 12, and 2, that's normal for tungsten. All right, so orbital electrons. So there's the centrifuge force and there's the attractive electrical force. So the centrifuge force causes the electron to fly out in space. So it's like throwing it past. And then the attractive force is a positive charge nucleus, and the negative charge electron, it tends to cause it to fly back together. So it flies out, and it does it not in a perfect circle, but it flies in a centrifugal pattern. So it's not a perfectly round. So these forces are exactly equal and opposite in a stable orbit. So the electrons are flying around the nucleus in a stable pattern. So if we look at the electron binding energy, it's measured in electron volts. So it's the energy of one electron when accelerated by 1 volt. So binding energy decreases as the distance from the nucleus increases. So as we go further away from the nucleus, the binding energy is decreased. So binding energy of these elements are important in what we're going to be studying in ionization. So we look at hydrogen, carbon, and oxygen. So the periodic table has 92 naturally occurring elements, 18 elements that are created in the lab, but we produce. In the upper left-hand corner, it's listed in ascending Z number order. In the upper right-hand corner is your atomic number, and below the elements is your atomic mass. Your horizontal periods indicate elements that have the same number of electron shells, so they're chemically stable. And the vertical groups have the same number of electrons in the outer valence shell. Doesn't mean that they're stable. So valence, so it's the chemical combining characteristics, describes how an atom will bond with other atoms. So if it's going to give up an electron or gain an electron. So it's going to determine if it's positive or negative. Okay, the octet rule. So atom never has more than 8 electrons in its outer shell. For this reason, some atoms begin to fill in the next shell before the maximum shell number is reached. Remember how I said it was 2, 8, 16, 32? So that is what we're talking about, and we'll cover that a little bit more in class. So atoms with the 8 electrons in the outer shell is chemically stable or inert. So different types of energy. So energy is the ability to do work. So if you look at a physicist's definition of work, it's work equals force times distance. So force acting upon an object over a distance expends energy. Mechanical energy is the action of physical movement. There are two types. There's potential and kinetic. So energy that an object has because of its position. So if you have a slingshot, you have a lot of potential energy. And kinetic energy is energy of motion. So an object that is in motion is able to perform work because it is already moving. So there's chemical energy. Energy is released from a chemical reaction, such as the body converts chemical energy from food to mechanical energy for movement, and a battery converts chemical energy to electrical energy for its use. Heat energy is also known as thermal energy, results from movement of molecules. Temperature measures thermal energy, so a toaster converts electrical energy to heat energy. Electrical energy, so it's electricity, so results from movement of electrons in a conductor. So we're going to talk more about that as we go through circuitry. So a light bulb converts electrical energy to light. Nuclear energy, so it's attained by breaking bonds between particles within the nucleus. So nuclear power plants convert nuclear energy to electricity. Then you have your electromagnetic energy, EM. So it's a combination of electrical and magnetic fields traveling through space. So as you can see here, so the direction of the photon travel, and then you have a magnetic field, which is your blue, and your electrical field. And we're going to talk more about that in our hand rules and all that good stuff. So EM energy results from acceleration of a charge. EM radiation can travel through a medium or a vacuum, and if it does, it's a constant, and it's considered the speed of light, and that's with the lowercase c, and it's 3 times 8 times 10 to the 8th meters per second, so 186,400 miles per second. Yes, you're going to have to know that. And then your book talks about the wave-particle duality and excitation and ionization. Definitely read about those because it is what we are studying. I'm not going to go into detail in this PowerPoint. So, characteristics of EM radiation. We have wavelength, energy, and frequency. So, we look here, we're going to go into each one. Waves are disturbances of a medium, and so ocean, sound, and wavelength is distance between two consecutive points on a wave. So it's a crest to crest. We have frequency is the number of waves that passes in a particular point in a given time frame. So the number of cycles per second. So it's measured in hertz. The wave equation is frequency and wavelength inversely related. Velocity equals the frequency times the wavelength, and velocity of all EM radiation is constant, so it's 3 times 8 meters per second. All right, the particle theory. We have high frequency, high energy EM radiation interacts like particles when contacting matters, not like a wave. So the wave theory has sound waves, and we've got all of our different waves, where this is the particle theory, where it's more like moving in a straight line instead. Photon energy and frequency are directly related. If frequency is doubled, the energy doubles. So there's your equation right there, and it talks about Planck's constant. So E equals H times V. So E is the photon energy, H is Planck's constant, is 4.15 times 10 to the negative 15 electron volts per second, and V is your photon frequency, which is also the gamma wave sign. So Planck's constant, he's a German physicist, and he has his equation is E equals H times V. So H is 4.15 times 10 to the negative 15 electron volts per second. All right, so discovery of X-rays. You should already know this. Wilhelm Conrad Röntgen, 1895, first Nobel Prize in Physics in 1901, identified the use of barium plantinoside. So, X-ray properties. They're penetrating and invisible form of EM radiation. They're electrically neutral, polyenergetic or heterogeneous energies. So they can come out in one energy or in multiple different energies. They release heat when passing through matter. And the properties are, and you need to know these, They travel in straight lines. They travel at the speed of light in a vacuum. They can ionize matter by adding or removing electrons, can cause fluorescence in certain crystals, and cannot be focused by a lens. So, X-ray properties, they affect photographic paper or film. They produce chemical and biological changes in matter through ionization and excitation. That's where the problem arises. They produce secondary and scatter radiation. So the scatter radiation, secondary and scatter are what expose the patient and us as workers. So in summary, there's a lot of different branches of science that we just talked about. So look at matter and energy and the basic structure of matter, basic concepts of atomic theory, the types of energy, EM spectrum, and properties of X-rays. So it's important that you're able to understand this basic foundation, because we're going to take this foundation and we're going to build upon it. So make sure that you learn about it. That's our lecture.